we don't always have to generate the input coordinates for a molecule on our own, right? Especially if, they're well known. So one of the resources that we can easily use to generate input geometries from actual experimental data, right, from crystallographic data, is using the CSD database, right? So one option is to use WebCSD. The other option is to use the CSD software, right? And so that software that we would use is Conquest. So if we open up Conquest, what we can do is we can draw whatever molecule we're looking for. And so if we have the full database installed on our computer, right, we can just easily check it there. And that actually goes a lot faster than doing WebCSD, but sometimes, right, you may not want to have 12 gigabytes worth of crystallographic data on your computer. So that's understandable, right? So you would have to then, use the WebCSD approach in that case, right? So this is how you would do it with Conquest. So we could just simply draw the molecule. So that what I'm going to be doing is tempo. So right, you can easily add in those coordinates right there. Oh, it's not coordinates, sorry, right? The 6-membered ring. I'm just going to throw in then the methyl groups off of those carbons, change that out to a nitrogen, right? Change this out to an oxygen, right? So you can, build it however you want to. And so if we were to take this right here and we were to search, what we want to make sure, right, is that we have 3D coordinates determined, checked, right? Because that's the entire purpose of what we're doing, right? We're not actually doing this database search to do some kind of broader data analysis, right? We're actually just simply trying to get the coordinates for a molecule. So make sure, right, you have 3D coordinates determined set, and then if you click on Start Search, right, it'll just really quickly go through, search all of the whole database, right? So we have 760 hits. That's a lot of hits. And if we're looking at this first structure right here, right, this isn't tempo on its own, right? This is, that framework that you have for tempo as, part of a bigger molecule, right? And if you go down, right, you start seeing that you have, variations of tempo, and again, right, larger frameworks that include the tempo, type of, structure in it, but it's not, specifically the one that we're looking for in this case. And so what we actually have to do, sometimes is we'll have to make everything a bit more specific, right? So if we go back to build queries and we draw out our structure, what we can do is, throw in methyl groups, throw in the nitrogen, throw in the oxygen right here, right? So what we can do is here under atoms, right, under hydrogens, right, we can say generate, hydrogens. And we can do that, we can choose which ones we would want to do it for, right? You can select specific atoms, or you can say, all atoms. So I'm just going to do all atoms. In this case right here, right, it does throw one onto the oxygen, so we can just simply change that back to being, it's not letting me. Either way, right? I mean, it doesn't matter for what we're going to be doing, but it automatically generated them all. So now when we search 3D coordinates checked, and we go in, right, we have only 11 hits in this case, right? And so what we can see right here is we can see, fully protonated, tempero derivative, right? We can see the salt in this instance, right? So you go through, and then you can find one that eventually is just simply tempo on its own, right? So you have, this as an option, and you have this guy as an option where it's just simply tempo hanging out by itself, and you have one where you have it together with a carbene, and you have it, here as the salt is again as well. So the one that, I'm just going to use is this, USI MUF one right here, right? Where it's just simply the tempo molecule with a hydrogen attached, which isn't a problem. So the next step that we would want to do now is we would want to open this up in Mercury. So here we would go to Visualize Structures, click on that. It's going to now open up, the Mercury software. And so now we have Mercury, right? So we can look at it. And so, there's 3 different tempo molecules that are actually part of this crystal structure right here. And so we only need one of them in this instance. And so what we can do is if we just simply click on, right, and select 2 of the molecules, right? So I selected 2 of them right here. We right click it. We can click on delete this molecule in both cases, right? And so it removes it. So now we only have 1 tempo molecule here, right? So this is a crystallographically determined geometry in this case. So it's very useful. And so, in our case, we don't want that hydrogen there, but we can take that out later. So, now that we have our target molecule, right, none of the spinach that comes with it is there anymore. We'll go here to File. We can click on Save As, right? And so then now what we have is an option to save what we have. And we're going to want to save it as a .mol file, right? So a .molecule file. And so I'm just going to refer to this as tempo H, save it to my desktop. And so now what we can do is if we go into WebMO, right, so I have it right here, the way that we would now use that geometry is here under new job, right, we would create a new job. And so we're at that point, right, where we can make our molecule. What we do now, instead of start building the molecule, we just click here on File, we click on Import Molecule, and then here, either you can, if you have different types of files, right, you can choose them. It does give the option for, to include the CIF format, but from my experience, it doesn't really do a good job of reading that out. So that's why I'm, suggesting to go through Mercury in all the instances to, generate the input file. So here we have the MOL file that we want. Here under Select File, click Choose File. So I have my file right here up top. I know I need to clean up my desktop. Right, so now it has all of the different coordinates and stuff like that in there that it would need. You click on OK, and so now the input geometry is in our WebMO thing, right? And so now what we can do is we can delete out that hydrogen, so we actually have tempo, right? The radical species in this case, right? We have that guy right there, and so now we can just simply submit our job the way that we'd want to. And so now when we're at that point, right? It's gonna go ahead and change this name, right? So tempo. Geometry optimization, B3 lip, def2 SVP, right? Now, one important thing to note it here is, right, tempo is an organic radical. So that means that it has one unpaired electron. So it doesn't have a charge, right? So this charge is still 0. The thing that's going to be different from what we've done in the past is change the multiplicity, right? So it's already selected the multiplicity for us. It's already said that it's a doublet, right? And so the way that multiplicity is calculated is based off of, the number of unpaired electrons plus 1, essentially, is how it goes, right? So a doublet, if you're thinking about like double, right, that means 2. That's telling us that the multiplicity in this case right here is equal to S equals 1. Or sorry, S is equal to 1/2, because, right, 1/2 spin in that case, right, so 2S plus 1 gives us, a doublet in this case right here, right, so a value of 2. Right, so triplet is 2 unpaired electrons, quartet is 3 unpaired electrons, and so forth. The next thing that we have to make sure that we do is we click on unrestricted here, right? So we're going to do an unrestricted calculation. What that means is that instead of treating all electrons as pairs within their orbitals, they will be treating them all as individual electrons, right? So it'll be either an up spin or a down spin. The way that it kind of relates that is it refers to it as either an alpha spin or a beta spin. These calculations take longer to do, right? Because you're now treating, instead of treating 2 electrons together as a single thing, right, you're treating each electron individually. And so obviously, right, that's going to at least double the calculation time. But it's necessary, right, to do these calculations. So here under advanced, right, change this right here to 32. And I believe I said to do Rij cosec in this case right here. So make sure that I also have the def2 SVPC. But either way, right, whatever the settings I have that I suggested in this case to do, now we just submit that. And so now it's running. And so now we just have to wait for this to finish.